Hello, I'd like to start by thanking the organisers for all the work they've done in putting together this event and for inviting me to give this talk. This talk is about the consequences of unitarity on cosmological correlators based on work from an upcoming paper with Enrico and Sadra that we labelled the Cosmological Optical Theorem. Cosmological correlators are the fundamental observable within cosmology. Whether it be the temperature of the CMB or the galaxy number density, we measure our observables by their statistical properties through spatial correlation functions. Within the inflationary paradigm, these perturbations from uniformity were seeded by a scalar field that fluctuated during a period of an approximately de Sitter expansion, and the perturbations to the scalar field were imprinted on the future boundary of this de Sitter space. So if we can understand how the physics in this inflationary period produced perturbations to the scalar field, and then how those perturbations grow into modern day observables, we can use observations today to infer what the physics was like during the early universe. This is similar conceptually to how we build particle detectors and observe the particles coming out of collisions in particle accelerators to infer the physics of the collision. However, this analogy goes beyond the superficial similarity in the nature of the calculations. In fact, the amplitude can be seen to cancel significantly from the apparent complexity of the diagrammatic calculations, and a similar observation can be made about correlators. Within the amplitude program, this cancellation was kind of culminated in the idea of the amplitude bootstrap, whereby the focus was shifted from individual diagrammatic calculations towards the wholesale calculation of the S matrix, known as the bootstrap program. Within this program, the symmetries of the underlying theory are used to infer directly the final form the S matrix can take. So first of all, the contact amplitudes are constrained by these symmetries. For example, the 3-point amplitude is fixed to take the form that I've outlined here. And then from this 3-point function, higher point correlators can be constructed by using the pole structure of the exchange diagrams, which is similarly constrained by these symmetries. If such a process was possible for correlators, then first of all we could massively simplify the calculation of high point correlators, which would be an achievement in and of itself. But it would also be able to make more concrete statements about early universe physics. So at the moment, if we want to see how a theory implants itself in modern day observables, we have to take that theory and perform all the calculations to look at the final result of the correlator. But if we could understand how, let's say, unitarity affects the evolution of these correlators, then we could look at our modern day observable and say, is this consistent with unitarity? And then if we saw it wasn't, then we would immediately have learned something new about the initial physics of the universe. Whilst I'm not saying I expect the physics of the universe to disobey unitary time evolution, this still represents a kind of unifying principle of how we could potentially be looking to explore correlators in the future. So the particular result for amplitudes that we're looking to extend, that we look to extend to correlators, is the optical theorem, which relates the difference of two amplitudes to this sum over products of different amplitudes. This is most useful when used in a perturbative calculation, order by order, where, for example, at contact level, the right-hand side can't contribute as each of the terms on the right-hand side enters first at linear order. And so the linear term on the left-hand side must vanish, and we conclude that the imaginary part of exchange of contact amplitudes is 0. And then also we can use this result to form cutting rules for exchange diagrams, which restricts the analytic structure of these amplitudes. So just to briefly outline the framework that we work in, we assume an approximately de Sitter universe, and this means that we take the de Sitter metric and the de Sitter mode functions, which are shown here. Nu is a constant that depends on the mass of the scalar field, and we then, however, allow departures from de Sitter through non-de Sitter invariant interaction terms, as well as by breaking boosts through the introduction of a speed of sound that differs from the speed of light. This therefore means that we've lost the very powerful constraints that are imposed by de Sitter isometries on the correlators. However, this loss of this power is necessary to have non-trivial correlators, as was shown by Green and Pyer. Just before I get into talking about some of these objects, I just would quickly like to define what I mean when I say the n-particle correlator, and perhaps more saliently, the coefficients of the wave function universe. So n-particle correlator is just the vacuum correlation function for n scalar fields that have been inserted in between vacuum states, and the coefficients of the wave function universe are the Fourier coefficients that appear when we expand the wave function of the universe in terms of these boundary fields phi bar, which are defined at the future boundary of de Sitter. So I'll begin this talk by motivating why we expect to see some cosmological optical theorem by discussing the poles of the correlator. I'll begin by looking at the established result of the total energy pole before going into some slightly newer results. I'll then look at a more detailed derivation of the cosmological optical theorem for both contact and exchange diagrams, and look at some corollaries of this result before discussing some potential future directions of this work. It's by now well established that all correlators contain a pole at the total energy, and the residue at this pole is related to the amplitude, as is shown schematically in this diagram. The order of this pole depends on both the number of fields and also the number of derivatives on each of these fields through the dimension of the operator at each vertex. I also show this in an algebraic form as well as this diagrammatic form, as we're not aware of this result elsewhere in the literature. And I'll briefly just define each of the terms here. As mentioned previously, Bn is the n-particle correlator, and An is the n-particle amplitude, defined for a flat space theory with the same interaction terms as in the de Sitter case. Then the additional momentum dependence comes from the KT pole, which has the order given as I explained previously, as well as some additional K dependence coming from the normalization mode functions. Finally, we get some powers of the Hubble, which enter with the number of internal lines, and as well as the number of derivatives at each vertex, as well as getting some extra terms from the number of fields. So we also showed this result continues to hold at the level of the loop integrand for diagrams that involve loops. This is perhaps a slightly more powerful result than it seems, as this is how the amplitude topology was about loops started. So in addition to these total energy poles, it was recently shown by Baumann et al. And independently confirmed by us that when you take the energy of any subdiagram to 0, you also find poles at which you can recover the amplitude. So again, we show this schematically here. And we see that it factorizes not just into the amplitude, but now we also get this additional term that is the difference of two correlators. The minus sign on the momentum on the right-hand side, on the line on the right-hand side, indicates that the opposite side of the energy enters into the expression. So again, I show this algebraically. The subscript L and R indicate the left and right hand sides, which is a kind of arbitrary distinction that we make in order to demonstrate that the energy of one subdiagram, which is the left subdiagram, is taken to 0. An equivalent result would hold if we taken the right hand subdiagram to be 0. The other thing to note is that these minus and plus on the right hand side are defined to come from diagrams that have an anti-time ordered and time ordered vertex. And so we only recover two amplitudes on the right hand side in the case that the term multiplying this bracket is real. Otherwise, we get a term that will depend on not only on correlation functions as defined previously, but also correlators that involve the contrary momentum. This is slightly different to the result as seen in Bauman et al.'s paper, where they were dealing with wave function universe coefficients. However, to relate their result to correlators, you would necessarily take the real part of this result, and you would end up with an expression just like this. So the fact that we see at these various different momentum configurations that we recover the amplitude from the correlator, and that at any of these points, if we were to apply any of the results that we know about amplitudes, for example, the optical theorem, we expect, therefore, we expect this result to come from the fact that there's some higher level relationship between correlators that at these momentum configurations simplify down to the optical theorem. And so to do this, we start off by splitting up the unitary time evolution operator into a constant part and a time-dependent part, and then sandwich this between two states, inserting the identity in the form of an outer product over some basis set of vectors on the right-hand side. This is the exact relationship that is used to derive the optical theorem in when we relate each of these terms to amplitudes. And so we look to relate these terms to correlators instead to form our cosmological optical theorem. However, as we saw previously, the left-hand side often ends up giving conditions on the imaginary part of some operator or some object, and as the correlator is explicitly defined to be real, it's potentially the case that we'll lose some information in exploring the consequences of this on correlators. And so instead we looked at the consequences on the coefficients of the wave function of the universe, as these don't have the restriction that they're always real. So we first of all, I will just outline the kind of steps required to relate each of the terms to correlators. So the first term on the left-hand side is inner product over this delta U, which is defined as shown on this slide. The important thing to note here is the introduction of the I epsilon term, which is introduced to regularize the integral at infinity by projecting us into the vacuum state, and this is required to prevent us the integral from diverging. And then we can straightforwardly relate the inner product of this term to the wave function universe coefficient for a contact term, as the wave function universe coefficient is just an almost identical integral, but with some additional normalization, a slightly different normalization term. The second term is not so simply related, as if we took the complex conjugate, we would have to switch the order of the bar and ket in the inner product. So instead, we start by changing the I epsilon prescription and moving it into the k-dependence of our mode functions through an analytic continuation. This achieves the exact same result of regularizing our integral at -infinity. We then use this property of the wave functions, which relies on the analytic properties of the Hankel functions. And it continues to hold for any operator that we would expect to find in entering into our theories, because they will either introduce scalar products of momenta, which won't be changed under this complex conjugation or the switching of the energies of our fields, or we will get terms like I times k coming from derivatives. And these terms will always continue to respect this property. And therefore, we can relate this inner product to the wave function of the universe coefficients evaluated at a slightly different value of the momentum, and then at the negative value of the energies, and then complex conjugated. So having performed this identification, we can then evaluate the right-hand side for contact diagrams, which will be 0 for the same reasons it was for amplitudes, because the right-hand side first contributes at quadratic order in any coupling constant. So we show this result diagrammatically here, as well as in an algebraic form. This result is then, the power of this result is best seen through examples. So first of all, we look at IR finite terms. So if we enforce scale invariance on our wave function universe coefficients, then for light scalars, i.e. those with a scaling dimension that is real, we find that the wave function universe coefficient is restricted to take the form shown here, which in turn implies this constraint on the function fn, as when we switch all the signs of momenta, fn won't change, ka over kt won't change sign. When we have arbitrary scaling dimensions, this imposes some constraint on the real and imaginary parts. Specifically, when delta takes integer values, it will this exponential will either give a plus or a minus sign, and so for massless fields, when delta is 0, this will always be a plus sign, and so the imaginary part of psi n is restricted to be 0. This is similarly the case if we have an even number of conformally coupled fields. However, when we have an odd number of conformally coupled fields, the real part of this wave function universe coefficient will be 0. Therefore, if we look to relate this to correlation functions rather than the wave function universe coefficient, then as the correlation function is proportional to the real part of the wave function coefficient, we actually don't get any information for massless fields or conformally coupled fields directly from this result, although the structure of psi n is still restricted somewhat, and so in certain cases we will still have some knowledge of how we expect the n to look. But when we have an odd number of conformally coupled fields and any number of massless fields in an interaction, then we find that the correlator will be uniquely 0. A further interesting case is when we take IR divergent terms. So for example, the interaction g phi cubed will give a wave function coefficient that looks like this. Note both the log term and then also some polynomial divergences. Most of the terms here will just vanish in our expression of the wave function universe coefficient, in the expression of the cosmological optical theorem. However, a fairly interesting cancellation also will occur, but from the fact that we change the sign in the log, which introduces an I pi term, and this term is what cancels with the imaginary part of the finite terms. And therefore, the cosmological optical theorem actually relates these two coefficients, and this can be seen explicitly here. The coefficients are the same. When we then introduce an exchange particle, the left-hand side of the cosmological optical theorem becomes slightly more complicated. The main reason for this is that the propagators that enter into the wave function universe differ from those that arise due to the time ordering of terms within the time evolution operator. However, they differ by a contact term, and so by the previous results, they will vanish on the left-hand side. And so we can just take the exchange diagrams to be related to the wave function universe coefficients in the same way on the left-hand side. While the right-hand side will no longer vanish, and instead we pick up terms that look kind of schematically as shown here. In terms of the wave function coefficients, we then get this expression. As long as the interactions are IR finite, and also if we restrict ourselves to looking at massless scalar fields, we can then relate this expression in terms of wave function universe coefficients to a very similar expression involving correlators. The reason for this is that on the right-hand side, these two conditions enforce that the wave function universe coefficient is real, and therefore the right-hand side, we don't have to deal with any terms that look like the imaginary part of these wave function coefficients. And so we just directly get the correlators. It also means that on the left-hand side, we can relate this complex conjugate term to a correlator, where there are some nuances in the case of IR divergent terms. An interesting point to note is that we can directly recover the subdiagram poles for this correlator term. So if we take the energy of the left-hand vertex, for example, to be 0, then the first term will be singular there, but the second term cannot have a singularity at this point. As if it did, then this would represent a singularity in the correlator at k1 plus k2 minus s, which is a physically realizable singularity. And therefore, we don't expect to find it in our correlators. If this means that any singularities on the right-hand side that come from physically realizable singularities will correspond to this second term on the left-hand side, whilst ones that come from non-physically realizable momentum configurations will come from the first term. On the right-hand side, the only term that will be singular when E left is taken to 0 is the first term in the first bracket, where this is its total energy. And so we recover its amplitude exactly as we saw previously. And we can similarly recover all the other poles in the correlator through this method. This is interesting both from the fact that the optical theorem exactly gives us this pole structure, but also as we've classified all the poles of all diagrams previously, we could potentially construct higher order cosmological optical theorems from this pole structure by individually finding each pole. And this could represent a way of kind of extending this to higher order diagrams. I'll just show how this optical theorem manifests itself in a single non-trivial check. We refer to this as a non-trivial check because first of all, it shows the generality of our result in that involves spinning fields, and also because just by observation of the terms, this relationship isn't, at least to us, very obvious. So the fact that it involves gravitons is perhaps surprising, as in our derivation we explicitly required scalar fields. However, this was only to ensure the correct analytic properties in time, and graviton correlators have the same analytic properties. The fact that we can apply it to both scalars and spin-2 fields suggests that it should be possible to find some kind of optical theorem for arbitrary spin. So the result that we expect to hold is shown here. just for some variety, we show the bulk perspective of the optical theorem, whereas previously we had a boundary perspective. The wave function coefficients are shown here, and do in fact satisfy the tensorial version of the optical theorem, which differs from the scalar version in that we introduce an additional sum over polarizations, the plus and cross polarizations, which are denoted here by lambda on the right hand side of the expression. Some points to note are, first of all, psi3 here is IR divergent, whereas psi4 is not. And so in the optical theorem, all these IR divergences cancel. Moreover, psi4 has a total energy pole in all of its terms, whereas psi3 can't know anything about total energy on the right hand side. And so in the optical theorem, all of these total energy poles have to cancel, which is perhaps a surprising result just looking at this term. So I will just conclude with some potential ideas for some future directions that we could take this work. First of all, we'd like to use these results to directly bootstrap 4-point functions from the known 3-point functions, just as we could do for amplitudes. However, with amplitudes, we additionally required some extra symmetries or extra conditions to be imposed, which came from locality and causality as well as Lorentz invariance. And so understanding exactly what implications these have for correlators may be necessary to perform this bootstrap, and would also be interesting in their own right to explore. We'd also like to extend this to particles of arbitrary spin and mass. So a lot of the time we restricted ourselves to just massless or conformally-coupled fields for the scalar case, although some of our results were for generic mass. Sometimes this generated this simplification was hidden behind the idea of IR regularity. And also, as we saw for the graviton, this applies to both scalars and spin 2 fields, so potentially we can find the result for arbitrary spin. An avenue we've also been exploring is that it may be possible to derive these results in a more natural and powerful way from the properties of the wave function and its symmetries, rather than having to refer to the form of the mode functions and performing time integrals. This would represent a way of extending this to arbitrary spin, as understanding just how the wave function behaves would be a more powerful tool. And finally, understanding this in a more like generic spacetime, so where we allow slower corrections, and also we allow deviations from scale invariance. This for more speculative models. Thank you for listening, and I look forward to hearing your questions.